AQA did a question on this a few years back, and it's quite a nice way of showing how having non-standard conditions affects the electrode potentials. Okay, so what we've got is we have got two, they look the same. We've got 2 beakers of copper sulfate with copper rods in them. Okay, the only difference is this one on the left is a lot weaker, a lot more dilute. It's only 0.1 mole per decimeter cubed, and the one on the right is the the standard concentration, 1 mole per decimeter cubed. So we know, let's call that one, let's call this E right, and so E left, that would be, wouldn't it? Yeah, E left and E right. Now we know that the value for E right has got to be plus 0.134 volts, because that's the standard conditions. It's 1 mole per decimeter cubed. But let's think about E left. Okay, so I'll just write the equation again. Cu2 plus 2E minus, this is Cu, we've got E left here. Now, the copper concentration is a lot lower than 1 mole per decimeter cubed. So Le Chatelier tells us that this equilibrium is going to be pushed in to the left to try and increase the copper concentration, copper 2 plus concentration. That means it is better at giving away electrons. That means the E value for E left will be more negative. It will be lower than the value for E right. So that one is plus 0.34 volts, and that one is less than 0.34, i.e. it's negative with respect to the right. So we can see there we're going to have the we're going to get a voltage difference, and so we're going to get electrons flowing out of the negative electrode, and it's going to light that bulb up, and it will flow into the right hand side. Okay, so the electrons will start flowing. So imagine we let this, if we allow this cell to run, what will happen eventually? Well, we can see here, eventually, well, what's going to happen to the copper ion concentration on this side? That's going to go up as the electrons are leaving the copper atoms, turning into copper ions, and the copper concentration on this side is going to go down. And of course, obviously, what will happen in the end is that you'll have equal copper concentrations on both sides, and then there'll be no voltage, and the current will stop. No voltage difference between those two electrodes, and the current will stop. And so it's almost like diffusion, isn't it? You know, where you've got ions moving from a higher concentration to a low concentration, because it's not the ions themselves moving, it's the electrons are going around, but it has the same net effect. And you get some useful work done in the process. And like, you know, if you think about biology, if you want ions to move from a high concentration, from a low concentration to a higher concentration, that's active transport, you're going to need energy for it. Well, this is the opposite of that. You're getting, you know, you end up the ions go from a high concentration to a low concentration. You get some useful work done indirectly by the electrons flowing. Okay, so that's quite a nice example, and I say they asked a question on that a few years ago. Here's another. Let's have another thing about another effect. Right, here we have to look at these two half equations. The top one is our standard hydrogen electrode, and of course the electrode potential for that is 0 volts by definition. Have a look at the lower one. Now, essentially, it's the same thing. If you look at both of them, what's the oxidation number of hydrogen is +1 on the left in each case, and you're forming hydrogen gas on the right, so it's 0. So essentially, what's happening? It's the same thing in both of those equations. What is changing, of course, is the pH conditions, or the ion concentrations. Right. Let's just remember Kw. Yeah, Kw is equal to H plus conc times OH minus conc, and that's always, well, at 298 Kelvin, it's going to be 1 times 10 to the minus 14, those units there. Right, let's have a think about this top equation here. Now the voltage is only 0 volts when the hydrogen ion concentration is the standard. Okay, so the hydrogen ion concentration is when hydrogen ion concentration is equal to 1 mole per decimeter cubed, the voltage is equal to 0. Let's write the electrode potential. The electrode potential is 0 volts. Right, now imagine if we lower the hydrogen ion concentration, what's it going to do to the position of this equilibrium? If we lower it, the equilibrium is going to move that way. So that means it's better at giving out electrons. So it's going to become more negative. The E value will become more negative. So here, with low hydrogen concentration, we can see E becomes more negative. And the lower we make the hydrogen ion concentration, the lower and lower the electrode potential is going to be, the more negative it is. Now, eventually, if we get the hydrogen ion concentration so low that it's equal to 1 times 10 to the minus 14 moles per decimeter cubed, because of our value of Kw, which we got up there, yeah, so the product of that means the product of hydrogen ion concentration and hydroxide ion is always 1 times 10 to the minus 14. So we know if H plus is equal to that, then OH minus concentration is equal to 1 mole per decimeter cubed. So what I'm saying is take this to the extreme, where you lower hydrogen ion concentration so much that in fact it becomes alkaline, then you have that equation there. Okay, and the concentration of, the standard conditions for that one, you've got hydroxide ions, and it's the hydroxide concentration must be equal to 1 mole per decimeter cubed. And we can see, we've said that if you lower the hydrogen ion concentration, you're going to lower the electrode potential. Well, if you carry on, take it to extremes, you find there that it will go to minus 0.83 volts. So just to summarize that then, we can see if we go from that 0 value to that minus 0.83 value, what we're doing is we're reducing the hydrogen ion concentration. And if you reduce it to this extreme value where it becomes alkaline, with 1 mole per decimeter cubed OH minus, the lowest it gets to is minus 0.83 volts. Okay, I'm going to leave that one there.